Synthesis of Amphidinolide J. Cancer-fighting Amphidinolide J. Amphidinolide J is derived from extracts of marine dinoflagellate Amphidinum. Amphidinolide J shows specific cytotoxic activity against murine leukemia and human epidermoid carcinoma cells with an inhibitory maximal concentration of 2.7 micrograms per milliliter and 3.9 micrograms per milliliter, respectively. It is also a 15-membered macrolactone polyketide bearing 6 stereocenters, 3 disubstituted double bonds, as well as a methylene unit, which is a common structural feature encountered in almost all amphidinolides. Below is the reference used for this research, found in the organic letter and is in the RSC format. Reactions. Our focus today is the formation of the C4 and C5 bond. The C4 and C5 bond is formed by a B-alkyl Suzuki-Miura cross-coupling reaction. An alkenyl iodide reacts with a boronate under palladium catalysis, allowing us to join the two fragments cleanly and forming that key carbon-carbon bond that allows us to form that final structure, amphidinolide J. So before we can do the Suzuki coupling reaction, we need to be able to form the alkyl boron reagent. We can do this by use of tert-butyl lithium and 9-BBN. On the left here, we have fragment B. The key feature we care about in this is the alkyl iodide. We want to be able to convert this carbon, right where this iodine is attached, into a boron-containing group so that we can do the Suzuki-Miura cross-coupling reaction without any issue. So the first reagent that we are going to add is that tert-butyl lithium. So tert-butyl lithium is extremely strong and very reactive. It can perform a halogen-lithium exchange. In this, iodine will leave and lithium will take its place. At that point, we would have created an alkyl lithium intermediate. This new bond is very nucleophilic. Next, we will add 9-BBN. This reagent contains boron, which is very electrophilic and will absolutely love the nucleophilic alkyl lithium. The alkyl lithium attacks the boron and replaces the methoxy group. At this point, we've created that new carbon-boron bond, creating the alkyl boron reagent. Now that we have this alkyl boron fragment, we can get ready for the Suzuki coupling. At this point, the alkyl boron reagent will react with the iodide fragment form under palladium catalysis. And like that, we have that C4-C5 carbon-carbon bond, producing fragment 16.
The key carbon-carbon bond in amphidinolide J is the C4-C5 linkage formed through a B-alkyl Suzuki-Miura coupling between the C1-C4 alkenyl iodide fragment and the C5-C12 boron substituted fragment. This step is both highly selective and essential to assembling the molecule's carbon framework. The catalytic cycle begins when palladium Cl2 dppf is reduced in STU to the active palladium 0 dppf triphenyl arsine complex. Palladium then inserts itself into the carbon-iodine bond of the alkenyl iodide, forming a palladium 2+ complex that bears both alkenyl and iodide ligands. This oxidative addition increases palladium's oxidation state from 0 to +2 and determines the regioselectivity, ensuring the new bond forms precisely at the carbon that originally carried the iodide. Next, the alkyl boron fragment, prepared earlier by reacting alkyl iodide with TBULI and BOMe 9-BBN, is activated by the base CS2CO3 in a water THF-DMF mixture. The hydroxide generated in STU coordinates to boron, producing a tetrahedral borate species. This activation increases the nucleophilicity of the carbon-boron bond, priming it for transmetallation with the palladium 2+ complex. During transmetallation, the alkyl group transfers from boron to palladium, displacing iodide as an iodide anion, which can combine with cesium to form CSI in solution. The resulting palladium 2+ complex now carries both coupling partners, the alkenyl and the alkyl groups. As the triphenyl arsine ligand stabilizes this intermediate by suppressing the beta hydride elimination, which helps preserve the integrity of the alkyl fragment. Finally, reductive elimination occurs. The alkenyl and the alkyl ligands couple to form a new carbon sp2 and carbon sp3 bond between carbons 4 and 5, shown in red. Palladium is then reduced back to palladium 0 state, coordinated to dppf and triphenyl arsine, regenerating the active catalyst. Overall, the reaction is regiospecific because coupling only occurs between the iodide-bearing carbon of the alkenyl fragment and the boron-bound carbon of the alkyl fragment. It's also stereospecific. Oxidative addition and reductive elimination proceed through concerted 3-center transition states, giving retention of the E geometry of the alkynyl iodide. Additionally, the existing stereocenters within the alkyl fragment remain unchanged, as beta hydride elimination is effectively suppressed. In conclusion, this beta-alkyl Suzuki-Mayura coupling provides a regio and stereo-controlled route to the formation of the C4-C5 bond, setting the stage for the final macrolactonization that completes the total synthesis of amphidinolide J. Thank you for listening.